Hello friends, I am Dr. Rajesh and I am again with you with my second video on vector calculus. So in this video we will be studying two important theorems, and the first theorem is prove that the necessary and sufficient condition for a vector function f of a scalar variable t to have a constant magnitude is this one. So we will prove it. Let f is equal to ft be a vector function of scalar variable t. Okay, condition is necessary. Condition is necessary. Firstly, let us suppose that f has a constant magnitude. Let f has a constant magnitude. This implies that f is equal to constant, its magnitude, and the magnitude of f is sometimes simply written as f. If we put arrow over f, then it is a vector, and if we simply write f, then this is the magnitude of the vector. So this is the shorthand notation for scalar quantity. Okay, we may be using this very frequently. So this is a constant quantity. If f is a constant quantity, magnitude is constant, then its square is also constant. Constant square is also constant. And we know that f dot f is equal to f square, which is a constant quantity. This is a result that f dot f is equal to f mod square. This implies that f dot f is equal to constant quantity. Now differentiating both sides with respect to t, we get and differentiation of constant is 0. Differentiation of constant is 0. This implies that now applying the differentiation rule in dot product, we will keep the first function as such and we will differentiate the second, then we will differentiate the second, and then keep the second function as such, and differentiation constant is 0. Okay, this implies that f dot df by dt plus f dot df by dt is equal to 0, because we know that dot product is commutative. Dot product is commutative. Commutative means a dot b is equal to b dot a. This implies that 2 f dot df by dt is equal to 0. This implies that 2 cannot be 0. 2 cannot be 0. If it has to be 0, this thing has to be 0. Okay, this is very much clear. 2 is a constant quantity. It can never be 0. So this is equal to 0. So we have shown that f dot df by dt is equal to 0. Okay, next we prove that condition is sufficient. Condition is sufficient. Let f is equal to ft be a vector function such that f dot df by dt is equal to 0. Required to prove f has constant magnitude, that is f is equal to constant, its magnitude is constant. Okay, now we are given that f dot df by dt is equal to 0. This thing is given. Multiplying both sides by 2, that we can do. You know that we can do. We have the authority to multiply with 2 on both sides. So this we have done. Next is, we can write it as f dot df by dt plus f dot df by dt. That we can do because 1 plus 1 is 2. Okay, this is simple. This implies that f dot df dt plus df dt dot f. In the second term, we have done that a dot b is equal to b dot a. Okay, in this second term we have commute the vectors. So this is first, this is second, this is commutative property we have used. This further implies that by differentiation of vectors dot product, we can write this is equal to this thing. This further implies that integrating both sides, we get this is equal to constant quantity. This implies that f dot f we know is that f magnitude square. This is constant, and if it is constant, this implies that square root of a constant is also constant. Implies f has constant magnitude. So this is the theorem we have studied, that f has a constant magnitude if and only if f dot df by dt equal to 0. So this theorem will be used in some questions, so we have to also keep the result in mind. So this is very important theorem. So one way it is condition was necessary, and other way it was sufficient. Now we study the next theorem, and this theorem is very important from the examination point of view. All students must note that there is 95% chances that this theorem could appear in the examination, and this is very important, the most important theorem among all the three theorems we have covered on the constant vectors. So this is the third theorem, and the statement of the theorem is given by: the necessary and sufficient condition for a vector function of a scalar variable t to have a constant. Now the last theorem was about the constant magnitude, and there was f dot. Now it is about constant. The necessary and sufficient condition for a vector function of scalar variable t to have a constant direction is this one. Here is cross, and direction is to be constant. So this theorem is very important from examination point of view, and this is, I'm going to mark it as important theorem. So now see, let us suppose that first let f is equal to ft be a vector function of scalar variable t. Let f cap be a unit vector in the direction of f. Now see what we have done. This is a vector. Okay, this is a vector, and we have taken a unit vector in the same direction, and this is named as f cap, and this thing is named as f vector. This is a unit vector. Unit vector is a vector that has a unit magnitude. This has constant magnitude, this has unit magnitude. So magnitude, it is equal to f cap is equal to 1, and it is in the same direction as that of f. Both have same direction. Okay, so we have assumed that f cap be a unit vector in the direction of f. Then by definition of unit vector, we can write f cap is equal to f divided by f magnitude is equal to f, and f magnitude I have without arrow over the head, it is the magnitude. This is representing, because I am again saying it is a shorthand notation, f vector magnitude is equal to f. This implies that now cross multiplying, this will go over there, so this implies that f vector is equal to f cap. Now differentiating both sides, we get differentiating both sides with respect to t, we get df by dt is equal to d by dt f cap. Now using the product rule, f will be as such d f cap dt plus now df by dt f cap will be as such. This further implies that f taking cross product on both sides from with f from the left side, okay, so that is what we get, df by dt f cap. And from equation number 1, we know that f vector is equal to f cap f df dt plus df by dt f cap by using 1. This thing is further equal to f into f is simply f square, and now see this f, this cross, and this is also vector quantity, so cross is for vectors, so this f will be out, f square, this is a vector quantity, this is a vector quantity, so cross is between the vectors only, so we will write f cap cross df dt plus, okay. Now next is, this is f, this is also scalar, so this will come out of the cross product, so this will be f df dt, and inside is f cap cross f cap. And we know that cross product of two same vectors is 0 plus 0, because a cross a is 0. This is the result we know. So therefore we have proved that f cross df by dt is equal to f square f cap cross df cap dt, and you are going to name this equation as equation number 2. So we have this result number 2. Now we suppose that condition is necessary. Condition is necessary. Let f is equal to ft be a vector function having constant direction. Required to prove f cross df by dt is equal to 0. Now f is having constant direction, so you see the case, I am again drawing, this is the vector, okay, and see this is the unit vector. So what situation has become, this is a vector f, and now it is having constant, it is important to mention, it is having constant direction. So this is a unit vector, its magnitude is constant already, and if it is in the same direction as that of f, so its direction has also become constant. So we can say that this f cap has become a constant vector. It has having constant magnitude 1, and now direction is parallel to this one. This is constant direction we have taken, assumed. So this f cap is also having constant direction, so its magnitude was already constant, so this will be a constant vector now. So I am mentioning this argument since f cap is parallel to f. This implies that f cap is also having constant direction. Therefore f cap is a constant vector. Okay, and from the very first theorem that we did on the vectors, that if any vector is constant, then this implies that df cap by dt is equal to 0. Now using in equation 2 this thing, if we use over here, so this will be 0, and anything taking cross product with 0 will be 0. Using this into f vector df by dt is equal to f square f cap cross 0 vector. It's actually differentiation of f with respect to t is again a vector, so it can be, if it is not written, it is obvious that it will be a 0 vector, and cross product taken with 0 vector is a 0. So this implies that f cross df by dt is equal to 0. So one way we have proved. Now next is condition is sufficient. Let f is equal to ft be a vector function such that f cross df by dt is equal to 0. Required to prove that f vector has constant direction. Okay, since this is 0, and you may name it as equation number 3. So using 3 into what is 2, you look at equation number 2. This is equation number 2. So this thing is 0. So this thing is 0 means this is also 0. So this will be, I'm going to use 3 into, using 3 into, this will be 0. This is f square, this is f cap cross df cap by dt. Okay, this implies that, but f square cannot be 0, so this implies that f cap cross df by dt is equal to 0. So this is equation number 4. But we know that f cap is a unit vector. Therefore f cap has constant magnitude. If it has constant magnitude, then by the last theorem we can write that f cap dot df cap by dt is equal to 0. This is 5. Now see what is happening here. 4 and 5, look at equation number 4 and 5. What is the beauty of these equations is that this vector is exhibiting the property that its cross product with this is 0. Okay, fine. until here it is fine, but again see here its dot product with this vector is also 0. So this is how it is possible. This thing implies that two vectors are perpendicular, this thing is implies that two vectors are parallel. This is not possible, simply this is not possible. If this is not possible, so this is only possible, this is only possible if this vector df cap by dt is a 0 vector. And if it is a 0 vector, then integrating both sides we get, or from the first theorem, very first theorem, remember the first theorem, if the derivative of vector is 0, this implies that f cap is a constant vector. If it is a constant vector, I will once again recall the same thing, say this is a vector, okay, f, and f cap is the vector in the direction of unit vector, in the direction of f, okay. Now what is the situation here? See, we have arrived at a point where f cap is a constant vector, means its magnitude was already constant 1, now its direction is also constant, this is a constant direction and it is parallel to this one, so I can say that f vector also has a constant direction. So from here we can say that since f cap is parallel to f, this implies that f vector also has constant direction. Therefore we have proved that a necessary and sufficient condition for a vector function of scalar variable t to have constant direction is that f cross df by dt is equal to 0. So this is all I have from this lecture, and in the next lecture we will be studying the next important topic of vector calculus. So till then, take care, and this is Dr. Rajesh saying you goodbye. Thank you for watching.